Yeah, welcome all. TCS seminar at the Jagiellonian University. Today our speaker is Matthieu Rosenfeld from the Laboratory of Computer Science, Robotics, Microelectronics, and I think I've lost something in Montpellier.
Seems fine.
So Matthieu works on both sides of the barricade, which means in combinatorics and theoretical computer science. And the first time I heard about Matthieu is when I saw his really cute short argument bounding the non-repetitive chromatic number of paths. I believe, like looking from the title and from the abstract, that we will see a lot of this idea today. Thank you, Matthieu, for joining us, and please take it from here.
Okay, thank you. So thank you for the introduction and the invitation. So as you said, my goal today will be to present some counting argument that I will try to apply to different problems. So what I will try to do is just to give some idea of similar techniques which are famous, I think, or well known. Then I will try to apply this counting argument to two different problems, just to give you an idea of how it works. And then I will conclude by mentioning a few other problems to which it's been applied successfully. Okay, so let me try with this kind of what kind of argument it resembles. So I'm going to talk about local lemmas and other related things. First, or maybe this is, do you see the zoom bar on top? Is it fine?
Okay. No zoom bar, just the counter at the top right.
Okay, so most of you might be familiar with the probabilistic method from R-, which you use some probabilistic argument to prove some deterministic result, some kind of, maybe you're going to use some probabilistic argument to prove that there exists at least one object with some desired property or something like that. One of the most important tools from this probabilistic method that was introduced by R- is the so-called Lovász local lemma, which probably don't read the result, but suppose you have some collection of bad events that you want to avoid. You want to construct some object which does not have any of these bad events. Then under the condition that the probability of each bad event is at most p, and each of these bad events is not dependent on too many other events, which is bounded by d, if the following equation holds, where e is just 2.7 something, then the probability that no bad event occurs is non-zero. That is, there exists at least one object in your collection which has none of these bad events. And so this result has been applied to many different problems. Let me just mention one of them. I mean, maybe all of you are familiar with this, but let me just remind it. So for instance, so I'm going to take phi, a K-SAT formula, by which I mean it's a logical formula where I have a collection of clauses. I want each of my clauses to be satisfied, and each clause should look something like x1 and x2 and not x3 and x7 or something like that. Sorry, it's not an and, it's an or. Let me start again. So it's x1 or x2 or not x3. So we all know that this is an important object for computer science. This is central object in for NP-complete problems. And this is really hard to solve. Okay. So I have this K-SAT formula. And if I have just one extra condition, which is every variable does not belong to too many clauses, that is at most 2 to the k divided by ke clauses, then psi is automatically satisfiable. And this is a direct application of the previous lemma. I'm not going to give the proof, but just take some random assignment, compute the probabilities, and it works. So it's just a 3-line proof. I think the proof is shorter than the statement of the Lovász local lemma. So if you think about it, it's pretty strong because we have this problem which is known to be really hard. Can you satisfy a K-SAT formula? But now you have this pretty simple property to check that tells you, okay, the formula is going to be satisfiable. And it actually applied to a quite large collection of formulas. And okay, let me also mention the fact that this is almost optimal. This is optimal up to a factor of 2, which you can in fact get the optimal value, but you need a slightly more advanced version of the Lovász local lemma. So this is the first thing. There are many different versions of the Lovász local lemma, which can be more tailored to different problems, or simply more general. Now, the bad thing is, that's good. I know that my formula is satisfiable, but obviously, for this kind of problem, usually we just don't want to know that there is a solution. We want to build this solution. We want to obtain the solution. So it was open for a long time, whether one couldn't produce an algorithm to find the solution that the Lovász local lemma tells me there is a solution. And it was solved a few years ago. So Moser and Tardos proved that under the Lovász local lemma assumption, there is a randomized algorithm that finds a satisfying assignment in expected polynomial time. Let me not go into too much into the details. So this is quite an important result. They received the Gödel Prize for this result. And the technique that they used was later named entropy compression. And I think it comes from a blog post from Terence Tao, but it might be a bit older than this. Anyway, so we have this technique, which is called entropy compression, which is quite nice. And in fact, so not only does entropy compression tell you there is an algorithm that runs in expected polynomial time, but it actually improves the bounds in a few situations. Like there are a bunch of problems where you obtain better bounds with some version of entropy compression than with the Lovász local lemma. So people used it for different problems, SAT, graph coloring, hypergraph colorings, combinatorics and words, many different subjects. Okay, so we have these two different techniques, and there are actually other techniques that belong to the same space. So there is, let me mention in particular, the local cut lemma from Bernstein, which is a really strong tool. However, it's quite complicated, and I think that Bernstein is actually maybe the only person that used it. But this is quite powerful, but this is really hard to use, and people don't use it somehow. And then there is, for instance, cluster expansion, so this comes from a different point of view on these subjects. This really comes from statistical physics, so they are not really interested in the same thing, but somehow it gives you similar results to the Lovász local lemma. So there are many different points of view on this large family of techniques that apply to the same kind of problems. So the one I'm going to focus on today is a technique that we'll call the counting argument for this talk, which I introduced in 2020. So let me just say it's not completely true. The technique was actually known, maybe not this technique, but a similar idea was used in combinatorics and words for at least 10 years before that. But somehow people failed to generalize it. And it's actually not that hard to generalize this technique to graphs or hypergraphs or SAT or anything like that. Okay, so what I will do in the next slides, I will present this counting argument by applying it to two different problems. So let's do that. Okay, so the first problem I want to look at is proper hypergraph colorings. So let me just remind the definition that might be useful. So I'm going to say that the coloring of the vertices of a hypergraph is proper if no edge is monochromatic. So for instance, there I have a hypergraph, which all of the dots are the vertices and the bags correspond to the set of edges, the hyper edges. And if we look at this coloring, I have some vertices which are orange and some are green. And there is something wrong because there is an edge which is monochromatic, right? This edge contains all the vertices of the same color. So this is not a proper coloring. Now, if I look at this coloring, this is a proper coloring of my hypergraph because each hyper edge contains at least two different colors. Okay, so naturally, I have a notion of coloring. So there is the associated notion of chromatic number. So the chromatic number of my hypergraph is just the smallest number of colors that I can use to properly color this hypergraph. Now I can define, let me just give two more definitions that are going to be useful. So the degree of a vertex is just the number of edges that contain this vertex. So you can see a few examples there. Okay. And I'm going to say that an hypergraph is R regular if every edge is of size R. So for instance, this hypergraph is 4 regular because each of the edges contains 4 vertices. Okay, so just before giving a formal statement of what I want to prove, let me just make some really informal remark. I want to relate the chromatic number of my hypergraph to the degree and to the regularity of the hypergraph. And so intuitively, if the degree of the vertices increases, this means that each edge each vertex appears in many edges. So it's going to be harder to use this vertex to fix a big proportion of the edges that contains it. Now, if on the other hand, if an edge increases on size, if it contains more vertices, then it's going to be easier to contain at least 2 different colors inside this edge. So basically, a large degree is not really good if I want a small chromatic number, and a small regularity is not really good either. So intuitively, yeah, smaller degree or larger edge means it's going to be easier to color my hypergraph. And so the formal statement I actually want to prove is the following, right? So, I mean, sorry, just look at this a minute. It's not really true, right? Because it really depends on the structure, but at least in general, if you want to prove some general equation, it seems to be a reasonable idea, which I can at least formalize in the following statement. So we have some quantity beta that can be anything. I mean, anything positive. So for now, just let's forget about beta. So I'm going to take a hypergraph, which is a uniform and of degree at most delta. Then what I can prove is that the chromatic number of H is at most beta plus delta divided by beta to the r-2. So somehow this gives some meaning to my previous remark. If the degree increases, then this quantity increases. And if R increases, then this quantity decreases, right? So intuitively, that makes sense. Now, the first thing that one could want to do is to optimize the value of beta to obtain the best bound possible. Let's not do that for now. What I want to do for now is to prove this theorem. So how do I prove this result? Well, first, let me just introduce 2 notation. The first one, I'm just going to introduce C, which is the number of colors. So I want to prove that if I have that many colors, then I can color my graph, whatever the choice of beta. And now, in order to do that, so the argument is called the counting argument, because I'm going to count the number of colorings, right? So I'm going to introduce C of H, which is simply the number of proper C coloring of H. And what I want to prove is to prove that there are many such colorings, because if I have many such colorings, then I have at least one such coloring. So this is the lemma that I'm actually going to prove. So again, there is H, which is a uniform hypergraph of maximum degree delta, right? Now, what I want to prove is if I remove a vertex from this hypergraph, and what I mean by that is if I remove the vertex, then I remove all the edges that contain this vertex, right? I look at the induced hypergraph. Then I'm going to divide the number of coloring by at least beta by doing that. If you look at it maybe the other way around, if I have a graph and I add a vertex and some edges that contains this vertex in such a way that everything seems fine, it's still uniform and it has maximum degree delta, then I'm going to multiply the number of proper coloring by at least beta. So now let's first notice why this lemma implies the theorem. Well, the empty hypergraph has at least one proper coloring. Now, whenever I add a vertex, I multiply the number of proper coloring by at least beta. So if I add size of H edges, then the number of proper coloring is at least beta to the size of H. Sorry.
So Matthieu, this statement, there is no dependence on delta, at least explicit in the what's going on?
Yeah, the dependence on delta is on C, right?
Oh,
yeah.
It's on C, of course.
It's hidden because I've fixed the number of colors, C, and then I'm looking at the number of coloring that use that many colors.
Oh, sorry, yes.
Yeah, it's a bit hidden. I've had this remark already in some previous talk. Yeah, so I have a number of colors which depends on beta and delta, and I want to prove that there are many such colorings. Good. So what I'm going to do in the next slide is I'm going to prove this. What I should say is this proof is going to be by induction. And yeah, and so introducing this statement is quite important actually. And this is maybe a weird statement. Like maybe someone could be satisfied with what I have there, right? It seems fine already to say that I have at least beta to the size of H coloring, but this is not strong enough. The proof is going to be by induction, and as usual, if I have something stronger to prove, it's actually going to be easier because I'm going to use my hypothesis inductively, right? So this is really the statement that you need. You need to say something about the way the number of colorings increases whenever you add one new vertex. This is important. This is half of the idea of the proof, is to introduce this statement. The other half is how you prove this. But what I'm going to do in the next slide is I'm going to prove this. So the slide is going to be a bit busy. I want to go slowly, and I really want to give all the details so that it makes sense what I'm going to do. Okay, so I want to prove inductively that whenever I add a vertex, or maybe whenever I remove a vertex and the related edges, I divide the number of proper coloring by at least beta. So first, let me just take care of again, I will do that by induction. So I have a natural induction hypothesis, which I will rewrite in a slightly more convenient way, which is now this should be true for H minus V and for every sub-hypergraph of H minus V by induction. So in particular, if I remove S vertices from H minus V, then the number of coloring is divided at least by beta to the size of S. And I'm going to use this at the end of the proof, but I just want to write it now so we can keep that on the corner for now. Now, how do we do the proof? Well, the idea of the proof is the following. I'm going to consider a proper coloring of H minus V. So I have a proper coloring of my hypergraph minus a vertex. And I want to see what happens when I'm giving a color to this vertex. So the first thing to say is, well, I have, say, C colors available. So I have C different ways to give a color to this vertex. Now, when I choose a color, two things can happen. Maybe the coloring is proper, then everything is fine. And maybe it's not. Then I'm just going to say it's a bad coloring because it's a bad extension. But really a bad coloring, so I have a proper coloring of H minus V, and the color I've chosen for V is bad. So I have the following equation, which is the number of proper colorings of H is at least the number of proper colorings of H minus V times C, because this is the number of colors I can give to V, minus minus the number of colorings where something bad happens when I've chosen the color for V. So this is what I want to bound. And to bound the number of bad colorings, I'm going to refine this into a more precise partition. And I'm going to introduce this notion of E bad coloring. So given an edge E that contains V, I'm going to say that a bad coloring is E bad if it is bad because it's monochromatic on this edge, right? Since I know that a coloring is, if a coloring is bad, it's because of V, so it has to be bad because of one of the edge that contains V. So every bad coloring is an E bad coloring for an edge E that contains V. So I have the following equation. The number of bad colorings is at most the sum over all the edges that contains V of the number of E bad colorings. So the thing that I want to do, and this is going to be the second important idea, is to bound the number of E bad colorings. How do I do that? Well, so let's fix some edge E, and let's look at some E bad coloring. So I have my hypergraph, and what I really care about is what's going on inside of E, right? So I don't really care of what's outside of E, but I know that E is monochromatic. By definition, it's an E bad coloring. Also, I know that if I uncolor V, then everything is fine. If I forget about V and all the vertices, all the edges that contains V, this is a proper coloring. So in particular, what happens if I just forget all the other vertices from the edge, except maybe one vertex W that I can choose beforehand. So I have a vertex W, I forget all the vertices of the edge E, I only keep W, and I look at this. So what can I say? I can say two different things which are going to be interesting. First is, this is the proper coloring of the remaining hypergraph, right? As soon as I've forgotten about V, this is a proper coloring. So this is fine. Now the second thing is, how many ways do I have to extend this into an E bad coloring? Well, there is only one way, right? Because an E bad coloring has to be monochromatic on E. So this is the only way to extend it into an E bad coloring. So what I said is basically, because of this, the number of E bad coloring has to be smaller than the number of proper coloring of the remaining hypergraph, right? So let me just write this. The number of E bad coloring is less than the number of proper coloring of H minus the number, minus E minus W, right? Which you can write precisely. And now I am done. This is it. Now I just have to do some computation and we will be done. So look at this. Basically, from this is the number of colorings of H minus V minus R minus 2 vertices, right? So E is an edge. So if I remove W and V from E, I notice this is of size R minus 2. So if I use my induction hypothesis, this means that the number of coloring of this is at most the number of proper coloring of H minus V divided by beta to the R minus 2. Right? Now I have a bounded number of E bad colorings, so I can try to use this to bound the number of bad colorings. So this is bounded. So how many summons do I have on this sum? Well, this is the number of edges that contain V, which is at most delta. So this is bounded by delta times this band that we've produced. Now that I have a bound on a number of bad colorings, I can try to use it on my previous equation. Let's do that. Pretty simple. So yeah, so number of proper coloring of H is at least this quantity. Now I just have to tidy things. I will just factorize by this number of proper colorings of H minus V. This is going to be on the bottom of the slide, right? So this is what I obtained. The number of proper coloring of H is this quantity times the number of proper coloring of H minus V. Now, what was my hypothesis? So you have to believe me now because I'm the only one who remembers, but I defined C to be beta plus delta divided by beta to the R minus 2 rounded up to the nearest integer, which means that C minus this is at least beta, right? So what I get is that the number of proper coloring of H is at least beta times the number of proper colorings of H minus V. And this is the proof. There are two things that I need to say about this proof. The first one is when I do the proof, actually, for most of the proof, I really don't care about any of my conditions, in particular the condition on C. The condition on C, it only appears in the end, which means actually I don't have to guess this condition. I can do the proof until the end. And then in the end, I need this to be larger than beta. So this is my condition. I need C minus this to be larger than beta. And this is the condition that I had on the previous slide. Yeah, so this is what I wanted to say about this proof. So I don't know if there are some questions before I go on. Otherwise, I will just keep going. Yeah, okay, so everything is fine. So yeah, so this is what we have proven. We've proven that the chromatic number of H is at most beta plus delta divided by beta to the R minus 2. So I can just try to optimize this by choosing the value of beta that gives me the best bound. In fact, we've proven something slightly stronger. We've proven that there are exponentially many such colorings, which is just nice as well. So I'm not going to try to optimize this quantity, actually. Van Lees and Wood did it, and this is computational, right? This is not really interesting. So Van Lees and Wood did this proof that I've given you, and they've optimized the quantity, and you obtain the following bound, which is the chromatic number of H is at most this quantity. And so what can I say about this result is, first of all, this is asymptotically optimal. And this is slightly better than a similar bound given by Erdős and Lovas in 75. In particular, this is much better when when R is small. When R is small, then this is much better than the proof given by Erdős and Lovas. When R is large, then this is pretty similar. In particular, there is one case which is really interesting. If you look at this statement, it's only true if R is larger than 2, right? Because otherwise something wrong is happening there. So let's look at the case R equal 2, right? R equal 2 is all my edges are size 2, so it's just a graph. This is, right, proper coloring of graphs. So let's look at this quantity. In this case, this part vanish, right? So I only have beta plus delta. So I need to optimize, I want to minimize beta plus delta where beta is larger than 0, which means this is delta plus 1. So I obtain that the chromatic number of graph is at most delta plus 1, which is optimal. And so what I want to say is you don't get this with the Lovász local lemma. What you get with the Lovász local lemma is much worse. You really don't get something optimal for proper coloring of graphs. So this is what I was saying, that basically this proof behaves better than the Lovász local lemma when R is small. Okay, so if you have some question about this, maybe you can ask them now. Otherwise, I will give my second example. If everything is fine, then okay, I'll go on. So let me try to apply the same technique to a second example, which maybe this is not the most interesting example by itself, star coloring, but this is a good example to how to apply the technique. So this is what I'm going to give it. So let me first remind the definition, because I suppose not everybody is familiar with this definition. Okay, so one way to define it is to say a star coloring of a graph G is a proper coloring such that any pair of color classes induces a forest of stars. A slightly more convenient way to define it. So this definition explains the number of star coloring. But there is a slightly more convenient definition, which is a star coloring of a graph G is a proper coloring such that no P4 is bichromatic. So whenever I look at a P4, I want to see at least 3 colors. Just to make things as clear as possible, let's look at an example. So I have the following graph, which is properly colored. So we could wonder, is it a star coloring? Well, it's not a star coloring because I have a P6, which contains only 2 colors. So this is 4 P4 that contains 2 colors. And actually, there is another one. Well, I mean, this is a P6, which contains, again, only 2 colors, but I can try to fix it by giving a different colors to these 2 vertex, and this should be a star coloring. Okay. Yeah, and again, I'm going to define the star chromatic number of a graph to be the minimum number of colors that you need to produce a star coloring of this graph. So let me mention some results about star colorings. Yeah, so if G is the graph of maximum degree delta, then Fertin, Raspo, and Reed proved that then 20 times delta to the 3/2 colors is enough to produce a star coloring. This was later improved by Andreka, Procacci, and Scopola, who proved the following bond, which is better. And just slightly after that, Espere and Paro improved it to 2√2 times delta to the 3/2 plus something small. Okay, so let me say something about this result, which is the kind of technique that they used, which is interesting to me. So Fertin, Raspo, and Reed, they used the Lovász local lemma and the most basic version of the Lovász local lemma, and they obtained the following bound. Now, Enrica, Procacci, and Scopola, in this article, they introduced some specific version of the Lovász local lemma, which is tailored to be good on a specific family of problems. And they applied it to different problems, in particular to star coloring, and they improved the bound. And then Espere and Paro, they used entropy compression to improve the bound. Yeah, so what I should say is there are actually somehow 2 different ways of doing entropy compression, 2 main ways of doing entropy compression. And this is one of the first articles to use the second way of doing entropy compression, whatever this means. I don't want to go too much into details. My point is, I'm going to prove this result again, and I'm going to prove it using this counting argument. So the proof from Espere and Paro is not given exactly, but if you write it directly, it should be 3 or 4 pages long, I guess. My proof is going to be 1 slide long, so this is going to be much shorter. Okay, so this is what we are going to prove. Before this, I just need to prove some useful lemma. So this is a purely structural lemma about graph of maximum degree delta, which is quite easy. So if my graph has maximum degree delta, and I look at some vertex V, and I'm interested in the number of P4 that contain this vertex, we can easily prove that the number of P4 that contain this vertex is at most 2 times delta cube. Okay, I should clarify, when I'm counting P4, if I look at the P4 in one direction and on the other direction, for me, it's the same P4, right? So how do we prove this? Well, we can look at this. Basically, the P4, I mean, the vertex V is either the first vertex of the P4 or the second vertex of the P4 by the symmetries that I've just said I'm going to use. And then when you fix this, how many ways do you have to choose the second vertex? Well, only delta ways, right? Because the degree is at most delta. Now, how many ways do you have to choose the third vertex? Delta minus 1 possibilities, right? Because one vertex is already used and then degree is at most delta. Same thing for the last vertex, which means that you have less than delta cube choices. Now, if you look at the case on the right, it's going to be quite similar. You have at most delta choices for this one. Now that this one is chosen, you have at most delta minus 1 choices for this one, and then at most delta minus 1 choices for this one. So again, you have at most delta cube choices. So in total, there are at most 2 times delta cube P4 that contains V. We are going to use this in a while, but I just wanted to make this right now, so we don't have to focus on this later. Okay, so let me remind you what I want to prove is the following. The star chromatic number of any graph G is at most this quantity. And what I'm going to do is going to be quite similar than the previous proof. First, I'm going to say, let's introduce number of colors. The number of colors is what I want to prove. Then I'm going to introduce CS of G to be the number of star coloring of G that use C colors. And finally, I want the following. I want beta to be such that C minus delta minus 2 delta cube divided by beta is at least beta. And again, you probably that you can guess how it will come. I will do my proof, and at the end, I will need this, basically. So this will be quite obvious where this bound comes from. For now, it might be a bit mystical, right? And what I will prove is quite similar, given a graph G of maximum degree delta, and any vertex V. If I remove the vertex V, then I divide the number of star coloring by at least beta. Again, the exact same idea. Yeah, so, and this implies that if my graph is of size n, then I have at least beta to the n star coloring of this graph. Again, the proof is going to be by induction on my graph. Okay. Okay, so I want to prove that if I remove a vertex V, then the number of star coloring is divided at least by beta. So let me just write the induction hypothesis right now. Actually, in this case, it's quite simpler because I can just write the induction hypothesis. I don't have to do something with it. Just the induction hypothesis is that if I remove one more vertex, then the number of star coloring is divided by beta. Okay, so we will use that in the end. Again, what I want to do is I want to look at the star coloring of T minus V, and I want to look at what happens when I choose the color for V. And I'm going to say, okay, and I'm going to do it slightly differently. I'm going to say, I choose the color for V in such a way that my coloring remains proper. But now that's it. That's the only thing I say. I want to choose the color on V such that the coloring remains proper. Now, two things can happen. Either this is a star coloring or it's not a star coloring, right? So this gives me the following equation, right? Because so the number of star coloring of G is at least C minus delta times the number of star coloring of G minus V. And this C minus delta comes from the fact that I want a proper coloring. So I know that there is at most delta colors that I cannot use for the property, for the proper coloring. And then maybe something goes wrong because I might have a P4 which is bichromatic, but then this is counted in the number of bad colorings. So now again, I want to count the number of bad colorings. And again, I'm going to partition this into a slightly refined set. So for every path P of length 4, so for every P4 which contains V, I'm going to say that the bad coloring is P bad if it is bichromatic in B in particular, right? So since every bad coloring has to be P bad for some choice of P, this means that the number of P bad coloring is at most, the number of bad colorings at most the sum of all the P4 that contains V of the number of P bad colorings. So now this is what I want to bound, and we're going to do something similar. let's look at a p-bad coloring. So on the right, this is a p-bad coloring. I have my path P and something outside. I don't really care what's happening outside. Yeah, so the first thing to notice is if I have a p-bad coloring, my coloring is proper, and I have at most 2 colors on my path. So basically, it can only look like this. It's going to be color A, color B, color A, color B, for some choice of A and B. Okay, so there is my vertex V. I'm only going to do the case where V is in second position, but the case where V is in first position is exactly the same, so I'm not going to do it. I'm going to just look at another vertex U, which I take to be the neighbor of V. So I have these 2 vertices that are going to play a particular role, and now I want to look at this coloring. I'm just going to forget U and V. So I remove them from the graph and I look at the coloring of the remaining graph. And again, it's going to be the same story. What can I say about this coloring? Well, this coloring is a star coloring, right? Because I've removed V. The only problem was because of V. So see, if I remove V, this is a star coloring. Okay, that's the first thing. And now how many ways do I have to extend this? Well, how many ways do I have to extend this star coloring into a p-bad coloring? Well, only one, because I can use only 2 colors inside this path and it has to be proper. So this needs to be blue or green, I don't know, and this needs to be orange. There is only one way to do this. So now the number of p-bad colorings is at most the number of star coloring of the remaining of the graph, which gives me the following equation. The number of p-bad colorings at most the number of star coloring of G minus V minus U. Now I can use my induction hypothesis that tells me that.
So sorry, this is really an inequality because not all proper colorings of the graph without V and U, it gives you a p-bad coloring because maybe the yellow and blue, if you repeat it, it's not proper, right? If you put it in. So
Yeah. So
that's why it's
this
inequality, right?
In most cases, it's going to be strict. That's what you mean, right?
Yes.
Yeah. It's even the case before, and there it's also the case because in many cases, when you're going to choose a bad color for V, it might be in at least 2 P4 that are both bichromatic. So this might also not be sharp. Yes. So none of these equations are sharp. That's true. Yeah, but somehow they are sharp enough. Okay, so the number of So I said the number of star coloring of G minus V minus U is at most the number of star coloring of G minus V divided by beta. And this is my induction hypothesis. Now, again, I'm almost done. I just have to put all the equation together. So it's going to look like the previous slide, the previous proof. So I have a bound on this part. How many summons do I have on this sum? Well, this is the number of P4 that contains V. And we've proven 2 slides ago that this is at most 2 times delta cube. So this is bounded by 2 times delta cube times this bound on the number of p-bad colorings. Now we can replace this on the previous equation, which means that the number of star coloring of G is at least C times number of star coloring of G minus V minus the bad coloring, which is at most this. Again, I've managed to produce this quantity on both sides, so I can factorize by this. So what I obtain is that the number of star coloring of G is at least C minus delta minus 2 delta cube divided by beta times the number of star coloring of G minus V. And now if you remember my previous slide, I said that I have one condition on beta, which is that this quantity is at least beta. So I can conclude that the number of star coloring of G is at least beta times the number of star coloring of G minus V. And this ends the proof. So the proof is quite similar to the previous proof, right? That's what I wanted to show today, is that this argument is quite general, and somehow I don't need many new ideas. This could be the case for some problem that you don't really have a bijection there, but you manage to find a bound, to express a bound on the number of bad extension as a function of the number of coloring of some smaller object. So this might work a bit differently, and it's the case in many applications actually. So this makes things a bit more complicated, but the core idea remains the same. Okay, so again, what we've proven is the star chromatic number of G is at most delta plus beta plus 2 delta cube divided by beta. And this is true for any positive value of beta. So we can try to optimize this, which in this case, it's not really hard because you probably know that when you want to optimize something like that, then you should take beta to be root of 2 delta cube. And so you get the following, which is the star chromatic number of G is at most this. And this is a proof which is really much simpler than Esperet and Parot proof of the same result. Okay, so it is, so I'm done with giving you proofs. I will conclude by mentioning a few applications of this technique which are more complicated, so I'm not going to do them, but to give you some idea of what it can be applied to. So let me mention this problem. I think this is the most interesting result related to this technique. So this is about the chromatic number of triangle-free graph of bounded degree, which is a question that has been mentioned a long time ago, right? So Wiesing already in 1968 explicitly mentioned the fact that we should try to estimate the chromatic number of graph without triangles and with a given maximal degree. Actually, the question is even older than this because in the 50s, people constructed different examples of triangle-free graph with large chromatic number. But in some of these articles, at least 3 of them, one by Erdős, one by Michalski, and one by Zykov, they say at the end, okay, graph without triangle can have absolutely large chromatic number, but maybe the bound in terms of the degree is still smaller than for any arbitrary graph. So this is a question that's a quite old question, right? And so there have been some progress in this question. There is some result by Scherer, for instance, which is quite famous about the size of independent sets and stuff like that. So I will skip some of these results. And I want to mention this result by Johansson, who in 1996 proved that any triangle-free graph G of maximum degree delta has chromatic number at most delta divided by log delta, which is much smaller than delta plus 1. Okay. And then in 2017, Molloy proved that actually the big O can be replaced by 1 plus small o of 1, right? So somehow the chromatic number of triangle-free graph is at most 1 plus a small o of 1 of delta divided by log delta. And we know that this is optimal up to a factor 2. And I think the lower bound is just given by the GNP for well-chosen value of P or something like that. I'm not sure, but I think it's not a complicated construction anyway. Okay, so let me, so about this result of Molloy, so what I should say is, the result from Johansson, it's proven by a technique which is called Rodel-Nibel. I'm not sure of the pronunciation. Anyway, the idea is somehow you take a really small part of the graph randomly, and you apply the Lovász local lemma to say that you can do something nice to this really small part, and then you do it again, and then you do it again, and then you do it again. And after some number of steps, maybe, I don't remember, maybe log n step or something like that, you can prove that the graph that you obtain now looks much better. And so you can do one more step of Lovász local lemma to finish coloring the graph. So somehow it needs to apply Lovász local lemma many times, like non-constant number of times. The proof of Molloy, and this is a really complicated proof, like really technical. You need to do really complicated things about concentration of probability and stuff like that, which is non-trivial to read and to write, even worse. The proof of Molloy is much simpler. It's still complicated, still technical, but it's much simpler, and it relies on entropy compression. Plus, I mean, a lot of technicalities, but like the core of the proof is one round of entropy compression. And now, quite recently, so in 2021, Bernstein, Brazelton, Kao, and Kang provided a proof of the same result using the counting argument. And the proof is much simpler. The proof is like 2 pages long, and there is no really advanced argument. So this is the proof that they provided. But actually 2 days later or 3 days later, I think, like this one was posted on the archive. 3 days later, Pirot and Hurley posted a proof of the same result on the archive. They also use the counting argument, but in a quite different manner. Actually, their proof is even simpler. And they obtain a similar result. So I should say that they also obtain other results. Like for instance, they say something about the number of solution. I told you, right? It implies that there is exponentially many solution. And in this one, they are really careful about this, and they can prove really good bounds on the number of solutions that you obtain, which are almost optimal. In the case of Pirot and Hurley, they later improved the archive version, and they obtained really nice result about the space of solution. They tell you how the space of solution is connected, what's the geometry of the solution space, and it's a really nice collection of results about coloring of triangle-free graphs. There is one more result by Martinson, which I think appeared a week later on the archive. It's really not really a new result. It's mostly what he did is he looked at the proof of Pirot and Hurley, and he really extracted the results specifically for triangle-free graphs. So he gives a 1.5-page proof of this result for triangle-free graph, and that's it. So it's just a short note that somehow gives an explanation of the proof of Pirot and Hurley. Yeah, so I think that's a really nice result. I'm not going to give any details about this, but this is nice achievement by these people. And so let me mention some other object has been applied to. So it has been applied to SAT formulas, non-repetitive coloring. So actually the first use of this technique outside of combinatorics and words was to non-repetitive colorings of graphs. This is what I did in 2020. Proper coloring of triangle-free graph, as I said, but you can apply it to frugal coloring, star coloring, many other graph colorings. So actually what I did when I introduced this technique is I tried to apply it to many problems that used entropy compression, and usually I obtain the same bound. I have a much shorter proof, which is easier to read, but I obtain the same bound, which is a bit disappointing because now what do you do with this result? You just have a shorter proof of a result which is already known, but still, I think it's at least quite nice. And sometimes you have better intuition of what's going on also. Yeah, and I want to mention in particular, so I said it in the beginning, or maybe when we were talking before, I did my PhD in combinatorics and words, and this is where this technique comes from. And actually in combinatorics and words, you can use this technique in conjunction with other really strong techniques. Like you can use this as well as linear algebra and automata theory, and then you get bounds which are as sharp as you want. So things which are almost decidability theorem and stuff like that. So this is really powerful in combinatorics and words. And I don't know how to extend these techniques. For instance, the one that uses automaton outside of combinatorics and words. It seems that there are good reasons for them to fail because some problem that it could solve in combinatorics and words are decidable when you look at the grid already. But it's a bit disappointing that none of this seems to work outside of combinatorics and words. So this is currently one of my projects to try to extend even more stuff from combinatorics and words to more general settings, say the grid or even graph theory. And yeah, so I also applied it to tilings and group theory and other combinatorial problems because it's quite general. Yeah, okay. So let me mention also this result from Van Les and Wood. So yeah, so when I gave this result, I concluded the article by saying this technique is quite general, it could be applied to many other problems. But the thing is, I wasn't able to give a general statement because it's not as convenient as the Lovász local lemma. Van Les and Wood managed to give a framework. So it's not as general as the Lovász local lemma, the result that they give, but you can apply it to all the problems that I've mentioned. You can prove them using their framework, more or less. Maybe not all of them, but at least the two I've did, you can. The thing is, so this is really nice. The thing is, just before giving the statement, you need to introduce the different notion that they have. Well, you need to introduce what is a beta C choosable hypergraph and all of these things, and just the definition to take a page, right? the definition take a page, the statement take half a page. So it's actually faster to just do the proof than to invoke their results. But I think it's a really nice result because somehow it gives you some abstract way of comparing these different techniques. Okay, so let me conclude on this. So on this counting argument, it is easier to use than entropy compression. And on some problem, it provides lower bounds which are better. And also it tells you something about the number of solutions. It doesn't give you any algorithmic result, which the entropy compression argument does, but it gives you a bound on the number of solutions, which is quite nice in some settings. There are many instances where it's easier to use than the LLL, and in particular, it's easier to optimize. Like people that know how to use the LLL, they usually know how to optimize a different variable that you need to optimize, but it's usually easier to optimize in my experience, at least in the instances where I try to apply it. And in some setting, it gives better bounds. Yeah, this is important. I should mention it. So in particular, the framework von Weinles and Wood, but more generally, in fact, this argument seems to be a particular case of the local cut lemma from Bernstein, which I mentioned earlier. And so the local cut lemma from Bernstein is much more general than this. However, the issue with the local cut lemma from Bernstein, as I said, is I don't think anybody else than Bernstein applied it. It's a really nice result. It's really strong. It's really deep, but it's really hard to understand what it says and the definition that you need to manipulate to apply it. Yeah, and as I said, in combination words, it can be coupled with other techniques to provide much stronger result than what it can do in more general settings. So I'm going to finish with this. Maybe you can try to apply it to your favorite problem. I would be really happy with this. Thank you for attention.